Hello, myself Dr. Vishnu Saran Das welcomes you to Chemistry Books and my video series on phase rule. Today we will learn derivation of Gibbs phase rule. So for this, let us consider a closed system consisting of C components C1, C2, C3, C4 up to Cc, and it also contains P phases like alpha, beta, gamma, del up to P number of phases, and each phase is in equilibrium with the other phase. So alpha phase is equilibrium with beta phase is in equilibrium with gamma phase. Each phase, the phases are in equilibriums. So for this, let us consider the Gibbs free energy of the system first. So for a closed system having phase C and phase P and C components, the free energy of each phase can be expressed as G of alpha is equal to F of T P Ni alpha, and G beta phase, beta phase, that is a function of Tp, Ni, temperature and pressure of the system remains constant. So gamma phase and up to P phase, so this is like this. And as the phases are in equilibrium, and we have to find the total free energy of the system. So the total free energy of the system is equal to the sum of the free energy. Say G is equal to the G alpha plus G beta plus G gamma up to plus G P. Okay, and for any change in free energy of the system is equal to the sum of free energy change of each phase. There is a number of phases, and Gibbs free energy change of the system is equal to the sum of free energy change of each phase. Okay, so that dg is equal to dg alpha, dg beta, dg gamma up to dg p. We have considered it is a closed system, so it is a multi-component system also. We can write for multi-component system dg is equal to minus s dt plus vdp summation over I equal to 1 to n mu I dni. So this mu I, which is the chemical potential. So I will tell what is chemical potential later on. So as T and P are constant, the phases are in equilibrium. So for equilibrium, the temperature and pressures are constant. So when temperature and pressures are constant, dT is equal to 0 and dP is equal to 0. So your SdT tends to 0 and vdP tends to 0. So your dg is equal to this much, summation of the mu I dni, where mu I is the chemical potential of the component I. So what is the chemical potential? Let me tell you. So the chemical potential is expressed as mu is dg by dni. So mu ni is equal to this when your temperature, pressure and other components 1, 2, 3 up to are remains constant, and this is the dni. Okay, so the change in free energy with respect to a particular component, when all other components remains constant and temperature, pressure also remains constant, it is called the chemical potential. Okay, so that chemical potential we have this is designated as mu I, and this is used here. For closed system, the delta G is equal to also 0. And so we have summation of mu I into Tni is equal to summation of mu I alpha for this alpha phase into Dni alpha, summation of mu I beta Dni beta for beta phase, and so on up to the p phases. So up to the p phases. So let this is equation number A. Let us consider this equation A. So closed, since system is closed, total mass of each component is equal and constant. So total mass of each component at equilibrium is constant. So we have another conditions here. So Dn1 alpha plus Dn2 alpha plus Dn3 alpha up to Dnc alpha is equal to 0. Similarly, Dn1 beta for beta phase plus Dn2 beta up to Dnc beta is equal to 0. So similarly, we can write a series of equations. So this is your p number of equations up to Dnp, Dn1p plus Dn2p. Okay. So the last equation will be your Dn1p plus Dn2p for p phase plus up to Dnp, Dnc, okay, because there is c number of components. So this is equal to 0. Okay. In order to, so say this series of equations is B. In order to equation B remains 0, so in order to make this 0 for all variations of n, subject to restriction of A. So this restriction is will be also there. Another requirement must be met. So in order to attain this condition, we have to subject to this condition, and we have another condition. Say, so that condition is your so mu1 alpha, chemical potential of component 1 of alpha phase is equal to chemical potential of component 1 in beta phase is equal to the chemical potential of component 1 in gamma phase, likewise up to p minus 1 phase. Because we have considered in the diagram we have seen. So this is mu1 for alpha and beta phase. This is mu2 for beta and gamma phase, and this is mu3 for gamma and del phase. Similarly, when we will reach here, this will be mu p minus 1. Okay, so this is mu p minus 1. And as the system is in equilibrium, so this is equal to this is equal to this is equal to this, and all these chemical potential of the same component in different phases are the same. That means the chemical potential of the different chemical potential of different components in each phase, the chemical potential of different components in each phase becomes equal. So mu2 alpha for component 2 is equal to mu2 beta is equal to mu p minus mu2 p minus 1. So p minus 1. So mu2 p minus 1. Okay. So similarly for C component, the mu C alpha is equal to mu C beta up to mu C p minus 1. Okay. So this is the relationship between the chemical potential and between the different phases, and our aim is to derive the Gibbs phase rule. So for Gibbs phase rule, we have to consider the number of components, that is C, and number of phases, that is P. So Gibbs phase rule is the relationship between the phase, component and the degree of freedom. So degree of freedom are the independent variables, and for this system, how many variables are there? Okay, so we have to consider the number of variables for this system now. Say we have the two external variables, temperature and pressure. Temperature and pressure, we have two external variables, so their number is 2. And we have C components, C1, C2, C3 up to CC, C components. So we have alpha, beta, gamma up to P phases. So total number of variations, that is C, P plus 2. This is the total number of variables is equal to the total number of variables of the system. So how many independent variables then? Then for the independent variables, we have to apply restrictions. Okay. So in the alpha phase, so how many restrictions are there in the variables? So for alpha phase, C1, C2, C3, C4 up to Cc. So the sum of the mole fractions of C1, C2, C3 up to Cc is equal to 1. So we can write x1 alpha plus x2 alpha plus x3 alpha plus up to xc alpha is equal to 1. So for alpha phase, this is one equation, and for beta phase is like x2 beta plus x1 beta, x2 beta plus x3 beta up to xc beta is equal to 1. So this is the number of equations, the number of relations. So this is for one phase, there is one relation. So there are number of P phases. So such type of equation we will get P number of such equations, and this is the P number of restrictions. Okay. So the number of dependent equations. So these are dependent equations. So this dependent equation number is P. Okay. So this is one restriction to be deducted from total number of variables. So another restriction, here we have seen the alpha phase in equilibrium with the beta phase in equilibrium with the gamma phase in equilibrium with the del phase. Okay. Similarly, so how many equilibriums are there? Total number of equilibriums are there. We have already derived, that is this is mu1, this is mu2, mu3 up to this is mu p minus 1. So number of equilibrium, the chemical potentials. So this is equal to this is equal to this is equal to this. Okay. So for each component, the number of equilibriums, that is p minus 1. For C components, how many equilibriums are there? So we have for one page, for one component, P minus 1 relations between chemical potential. So there are C components. So total number of relations. So for C components, that is the number of relations is equal to C whole into P minus 1. So this is one restriction. So the number of relations, this is one set of relations, and we had another set of relations, that is the P we have taken. The P is the number of relations between the mole fractions of different components in all the phases. So P number of equations, P number of relations are there. So this is one restriction and this is one restriction, and we have the total number of variables. Total number of variables we have already calculated, that is the Cp plus 2. Okay, so this is total number of variables, and this is one restriction and this is one restriction, or this is a set of relations and this is a set of relations among the components or the constant species in this system. So the number of independent variables, that is degree of freedom. Okay, so the number of independent variables, that is the degree of freedom, is equal to the total number of variables, say Cp minus Cp plus 2, and the number of relations, that is minus P and minus of P whole into, sorry, so we have the P minus C whole into P minus 1. So by solving this equation, we can have, the Cp plus 2 minus 2 minus Cp minus plus C. So this gives you the Cp cancels out, 2 plus C minus P. So here it is minus P. So this is minus P. Okay. So C minus P. Okay. So the degree of freedom F is equal to C plus 2 plus C minus P, or we can write this as the degree of freedom is equal to the F is equal to C minus P plus 2. Okay, or this is 2 plus C minus P. So plus and minus are separated. So in this way we have derived the Gibbs phase rule. So for Gibbs phase rule we have considered the Gibbs free energy and the chemical potential and the mole fractions of different components. So we have, first of all, we have reduced the number of total relations, the number of total variables in the system, and then the number of restriction, how many number of relations. The restrictions arises due to the relations between the components or constituents in that system. So this is a closed system, and so total number of variables minus the total number of relations gives rise to the Gibbs phase rule. So this is very interesting, and we have derived in a very simple way. So this needs a lots of fundamentals, that is the free energy, the chemical potential, etc. I hope you will enjoy this video and give your like and share among your friends. Thank you for watching this video.